Welcome to lecture 4.1. In this lecture, I'll be introducing the EAS reactions of benzene. Now, EAS stands for Electrophilic Aromatic Substitution, and I'll break that down shortly. First, let's revisit some familiar reactions. As discussed previously, when you take an alkene, an unconjugated or isolated alkene, and react it with HBr, you have the addition of a bromine to the molecule, as well as a hydrogen. That's in the Markovnikov position. Now, when we did this with a diene at room temperature, we still saw an addition, but it was a little more complicated. We generated this thermodynamic product, but we still added the bromine and hydrogen. The HBr still added to the molecule. However, when we react with benzene, nothing happens. Benzene is just too stable. Despite conjugated systems being stable, they can still react, but it really goes to show how stable benzene is that it does not react as if it's an alkene. With that in mind, let's take a look at the general scheme of the EAS reaction. How can we get benzene to react when it really doesn't want to? To do this, we need to use a catalyst. So the overall EAS scheme looks like this. Now, there are 5 reactions in this topic that we're going to focus on, but they all share a lot of very similar characteristics. And instead of memorizing, from this point in the course, there's going to be a lot of reactions that you need to know. And while there is some aspect of memorization that can help you, it's really important that you understand the similarities between certain types of reactions and understand how you can apply one reaction to another. These 5 reactions, studied individually, may seem like a lot, but I want to show you in this video that they're all very similar overall. The idea is that you take benzene, right, an aromatic ring, so that's the A in EAS, aromatic. You react it with some sort of electrophile. Now, an electrophile, that's something that is electron poor, that is going to be attacked. If you do this without a catalyst, the reaction does not proceed, right? Benzene is too stable to want to react with your standard electrophiles. That's why a catalyst is needed, right? The reason, since the benzene is therefore going to be attacking the electrophile at some point, that's the electrophilic aspect of the name. Lastly, we can see that in the product, the electrophile has now been added onto the benzene. But be careful, this isn't an addition. Notice that there was a hydrogen on that position previously on the benzene. Remember that every single carbon of benzene is sp2 hybridized and has 1 hydrogen. So really, it's been a substitution. We've substituted the hydrogen for the electrophile. And that is the last part of the name. Electrophilic aromatic substitution. How do we substitute a hydrogen for an electrophile on a benzene ring? This is a very critical question, as many pharmaceutical drugs, many bioactive substances, and other chemicals, I'm sure, involve these benzene rings. If they're not going to react for us, we need to make them react. So to do that, all these reactions are noted to share a common 3-step mechanism. Okay? The first step is that we need to somehow activate the electrophile. The benzene won't react with it by itself, so we need to dress it up, make it more positive, more attackable in some way to convince the benzene to do it. What is that step going to look like? Well, generally, and the interesting thing is this step won't even involve the benzene. We're going to have our electrophile. And again, there are 5 different reactions with 5 different electrophiles. These react with a catalyst of some sort. And the product of this step is to generate some sort of positively charged or otherwise more attackable electrophile. The idea being that benzene won't attack the original form, but after the catalyst activates the electrophile, right? This is kind of my shorthand, a positive electrophile, or AE for activated electrophile. Importantly, this step will be different for all 5 reactions. After all, those reactions add different groups, and so it makes sense that the activated electrophile will be different. What's interesting is that the next 2 steps are actually the same between all 5 reactions. That's a very useful thing to know. In the second step, benzene attacks. And what this looks like is benzene reacting with one of its pi bonds to make a bond to the activated electrophile. That would look something like this. Now, the product of this step is going to look a little different than our final product from the scheme. These double bonds will be untouched. However, one of these carbons is going to make a bond to the electrophile. However, when a double bond breaks, both carbons have lost a bond, so the one that didn't get the electrophile is going to be left holding a positive charge, or a lack of electrons. One thing to pay attention to is the location of the hydrogens. Right? There was one on both atoms, so the one that gets the electrophile is actually happy, but the one with the positive charge only has 3 bonds. So that's a carbocation. That's why it has a positive charge. Importantly, this is still a conjugated system. Right? Pay attention that this area here is a conjugated system, but we've now generated an sp3 carbon. Right? This is an intermediate. We've broken aromaticity. It's no wonder that benzene doesn't want to react. If we go back up to the scheme for a moment, we'll see that the benzene doesn't look like it changed. So in order to get the final product that's going to be stable and actually have a good reaction going, we need to make sure that we reform the aromaticity of the ring. And that's what step 3 is all about. So if I redraw this intermediate here, what's going to happen is we're going to leverage this hydrogen. A couple key things to pay attention to in terms of understanding this step. One, this hydrogen has to go. In order to get that product, we need to bring this carbon back to being sp2. That's going to reform aromaticity for us. Right? The second thing is that this positive charge also needs to get dealt with. And we can do this using an elimination-like step. So some sort of base is going to come by, and the base we use is going to depend on the reaction. We'll talk about the specifics later. Again, this is a mechanism that's going to fit all 5 of the reactions generally. That base is going to use its lone pair, or whatever it uses, to attack the hydrogen. That's going to break the carbon-hydrogen bond, and those electrons are going to be repurposed to form a pi bond. That's going to accomplish both of our goals. Drawing the product of this step in the mechanism, we can see that there's a new double bond that was formed from the electrons of that carbon-hydrogen bond. They are now present there, which has reformed our benzene ring and reformed our aromaticity. Now that the hydrogen is gone, right, the base has taken that hydrogen, all we're left with is the electrophile at that position. And that is the overall EAS mechanism broken down into 3 steps. First, activating the electrophile. That step's going to differ. And then the next 2 steps are going to look very similar for all 5 of the EAS reactions. Benzene will attack the electrophile that is activated, and then a base will come in to reform the aromaticity and remove that hydrogen. All in all, that is the overall mechanism for the EAS reactions. Now let's go dig deep into what those 5 reactions are and what functional groups we now are able to add onto a benzene ring. See you there.